that's there. Okay. All right. All right. I think we could begin. Why not? So, welcome back, everyone. Hope everyone's break went well. I hope it was nice and restful, and I hope it's not too hard getting back into the swing of things. Yeah. So today, we discussed in the first part prior to midterm 1, we discussed a bunch of stuff. We basically discussed all the major utilities that we need to create deep neural networks. We discussed gradient descent, optimization, all the cool little tools that PyTorch gives you so you don't have to write everything in NumPy. That's a huge boon. It'll make our lives a lot easier in the coming weeks. We discussed chain rule, computation graphs. So at this point, we know how to fit a function to a set of data, right? So now that we know how to fit some simple function to a set of data, and we have all the utilities that we need for that fitting, then the only place to go from here is to get more complex functions, right? So that's what we're going to do in the latter part of this course. We're going to discuss more complex neural networks, deeper, bigger, all that good stuff, different architectures, all that good stuff. And so today we're going to start off with a very simple version of a deep neural network that is a multi-layer neural network. Okay? So that's all we're going to do today. We're going to discuss construction of multi-layer networks, the usefulness of activation functions, why we need activation functions, and creating these multi-layer networks in PyTorch. Lots of example codes to do that. Yeah. And then the next time we're going to discuss convolutional neural networks, then recurrent neural networks, then Gaussian mixture models, principal component analysis, all that good stuff. It'll be fun. This is really the meat and potatoes of the stuff you're going to be tested on during interviews. So yeah, it'll be fun. Anyway, so where we last left off, we left off with PyTorch and like data loaders and optimizations. But slightly before that, we left off with logistic regression, right? That was the last classification model we discussed, and it works pretty well. So let's refresh our mind on what that was. Basically, we have basically a linear model, and we pair that with some logistic equation. We pass a linear model through a logistic equation, and that is what a logistic neural network is. That is what a logistic regression model is, right? So as we know, in the linear model, each of these components of Z are called logits. Okay, a little bit of that term. Remember that terminology that we discussed. So these are each one logical units, and then you pass these logits to a logistic model. So if we're doing binary classification, we could use the simple sigmoidal model. That's we used, I don't know, in countless lectures in the first part of this course. But if we're doing multi-class logistic regression, we use the softmax function, which is basically extending that sigmoidal model to multiple different classes. So for now on, we're going to pretty much do everything through softmax. So all we need to do is have a linear model that takes in a set of inputs x, and then it produces a linear output. And then we pass this linear output to the softmax function to get the probability that the probability that the model believes that a input belongs to a particular class Z, a particular class Y equals K. Okay, that's all we're doing there. So that's all well and good. We saw how well this works on many different data sets. And we created so many artificial data sets, especially with scikit-learn, to use softmax and to see how well it works in categorizing binary classes and more than binary, multi-class classes. Okay, so that's all well and good. You could return to those lectures if you need further proof that this works in some cases. But let's go on to a different example that we haven't seen before. Let's construct a new mode of data that isn't necessarily linearly separable. Okay? So, this code is too large, so I am going to jump out of the slide format a little bit. So, let's construct a new data set. And so all we want to do with this new data set is we want to create two classes that aren't necessarily linearly separable. Okay, we want to explore the limits of logistic regression. So, how do we create this data set? Well, we basically computed two circles and then added some random noise here. So if you want the actual code on how we created this data set, you could go here. It's a very simple calculation of a circle with some additional noise, and going around and having basically a center, a center for each, and then having a radius, and then basically plotting points along the circumference of the circle in a particular manner. Okay, so the actual computation of the actual construction of this data set is not necessarily important. What is important here is simply that there is no one line that we could draw to separate these two values, right? Because if we try to draw any line, if we, for instance, try to draw a line like there, we're going to get a ton of values that are misclassified. If we try to draw a line like there, we're going to get a ton of values that are misclassified, okay? So this is what's known as a non-linearly separable data set, okay? So this is important to note because there are optimization methods that require the a priori knowledge that a data set be linearly separable. We don't get into that in this course, but for instance, if you're doing support vector machines, certain schemes for support vector machines, notably hard margin support vector machines, that is a requirement that the data set be linearly separable, which this data set is not. Okay, when we did support vector machines, we basically discussed soft margin support vector machines. If you guys want to know more about that, I highly recommend Alex Schwing's course, Pattern Recognition. I think it's 544. He goes into this in great detail. So we have a data set that is not linearly separable. Now, not the end of the world necessarily, but it might make our lives harder. So let's go back here. Okay, so let's try out a logistic model, a logistic regression model on this data. And for the purposes of this exercise, we won't worry about creating a separate training, validation, testing splits. I mean, I know we discussed that last time with the data loaders, but in this case, this is just like a proof of concept, right? We're not actually trying to create a model that and we're not trying to create a model that will be released publicly. So let's recap what our logistic perceptron move is visually. I want to say node is visually, and that is a linear model, and that feeds into a logistic function. Okay. So this will be this is where we introduce a new term, which is simply a perceptron, namely a function that, namely this is a perceptron is simply a function that takes in a linear is simply, it takes in a logit and outputs the result of a particular activation function. This whole thing together is known as a perceptron. Okay? And so when we talk about multi-layer perceptrons, where we talk about basically having this perceptron feed into another perceptron, which feeds into another perceptron, which feeds into another perceptron. Okay? So that's what perceptron means. It's a very old term, I think, from the 60s. That when people first introduced regression models, that's the terminology they used. So we have this single perceptron, linear model, x1 times weight 1, x2 times weight 2, plus a bias. You sum them all up, you get a particular logit. You pass this logit into a logistic function, namely softmax. And so let's do that code. And if we do it, there we go, we get this. Kind of beautiful, kind of beautiful, but not ideal. But it makes sense, right? The whole issue with this data set is that it's not logistically it's not linearly separable, okay? And but we at our current moment only have a linear perceptron available to us, right? We have only this thing right here, that is a linear function that feeds into a sigma curve. So the barrier we're going to get is a straight line, right? That's the limit here. We can't get a curved line because this is literally the sum of x1 w1 plus x2 w2 plus b. So all we have is a single straight line, and when we feed it into the machine, it's going to try to make the straight line fit the data as best as it can, which it doesn't do too terribly, honestly. It starts off at a very high loss, and then we get sort of that exponential decay curve, and we sort of settle down at a particular loss value here as the model optimizes around the minimum. And the classification accuracy pretty much peters out around 87-ish%, which makes sense because the best thing that this could do is pretty much this line shows that it classifies all these points correctly, it classifies these points correctly, but there are just some points right at the ends that it can't manage to classify correctly. And yet, this is the best line because if we do a line in any other direction, if we have, for instance, a line like this, we're going to get way more values misclassified. If we have a line like this, we're going to get way more values classified. So the good news is the model is working as intended. The bad news is the intended function is not sufficient for what we want, right? Really what we want is a barrier that could curve itself around the class, right? That would be nice. So the question becomes, how do we get that? And specifically, let's look at the actual function. Let's look at the actual class. Let's look at the actual model class. So if we go to our two-layer model, which is, multi-class logistic regression, I am going to go back, multi-class linear regression. There we go. Multi-class logistic regression, sorry. Okay, so multi-class logistic regression, remember that it is simply a weight matrix. Basically, we have an input dimension and we have a number of classes, okay? So the multi-class linear regression is simply a matrix of is simply a 2 by 2 matrix in this dimension. And so the important thing to remember is that this weight matrix right here is literally this. Okay? And we have a particular bias because in our code we don't need to define the bias, we just set bias is equal to true, and so the PyTorch implements a bias there. Okay? So this whole model is this right here, these logics right here. Okay? So why am I emphasizing this? Well, if we know that Z is defined by, basically, we know that Z is equal to, or I should say Z1 is equal to W1 times X1, W1 W01 times X1, 0, W11 times X11. I'll make that sense. That'll make more sense in a minute. If we know this Z is equal to W1 times X1, or W1 times X plus B1, what we could do is actually plot the line. We could plot what the barrier is equal to. And that is, in fact, what we do right here. Thank you. Nope, not this one. Oh. Did my formatting? No, I know it's wrong. There we go. There we go. That is, in fact, what we do right here. Instead of just being like, okay, we're just plotting the probabilities and stuff, we could actually plot the barrier by looking at the particular weight matrix here and the biases and plotting what these are equal to. Okay? And all we need to do, it's probably a good thing to go to show you how to do that. I should have put the actual meat of that function here. I just put it all in one class, one cell. So all we need to do that is simply go into the model. We say, model, what are all the named parameters? We loop on all the named parameters. We look for the parameters that require gradients because there are many parameters that are just sort of bookkeeping stuff for PyTorch. So you want to look for the parameters that you're actually iterating on, and then you print those parameters there, right? So this is a very useful function because now we are able to look and actually plot the separation, the ideal separation that PyTorch optimizes to in order to separate one class from the other class. Okay? So to reiterate, the problem is that there is only one separation. And I should say there is one separation because since we're using softmax, there's one barrier for positive classes, and there's one barrier. We do one barrier for both, one barrier for positive case and the other barrier for the negative case. Okay? So we don't necessarily, if we did logistic regression, we could do a single barrier that separates the two classes, but we should get used to softmax. So the reason there's two is because there's two outputs. So because there's two outputs, there's two barriers there. Okay? So what we want, so the provided data set, the 2 moons data set, is clearly separable by a curvy line, but currently we only have a single straight line. So what do we do? Well, what if we have more lines? What if we have more separations and then we add them together? That's the idea behind multi-layer networks. And that's what we're going to do next. So let's try that. Let's try that. Go back into slide mode. So we'd like to implement barriers that aren't just straight lines, but are also curves. And let's, for a moment, just ignore training, ignore optimizations and stuff. How could we get a curve barrier going? How could we implement a curve barrier? So let's say we have the following code. Okay. Let's say we have the following code, and in fact, I have two particular types. I have two particular values that this weight matrix can be. This is the exact same. This is the exact same class that I did for logistic regression. I'm just trying to mess with the actual values directly. So I'm just setting up two different values, right? So let's go up and let's look at this first custom weight here. So custom weight values. So again, I'm not optimizing. This is just a random set of values that defines a particular set of barriers in the code, right? Straight lines, okay? So I have the weight matrix for the multi-class logistic regression. I have a set of particular values. I copy those particular values into the weight matrix. By the way, it's important you do things this way, because if you try to do things the other way by just defining by simply saying like this is equal to a tensor, then you lose a lot of the linear functions and all of that. You don't want to do that. So that's why I did things this way. I just copy the values into the linear weights. It works much better. So just a piece of code you might want to refer to later. So if we do the custom weights and biases, the first set of custom weights and biases, we could get we could get a particular boundary, or actually, let me real quick run I want to make sure that it's running correctly. Yep. My kernel. There we go. Yeah, okay. All right, just wanted to make sure. I restarted the kernel right before class, so we have so for the first set of values, custom weights and biases 1, we have a particular line, right? A particular line, not the optimal one. It's not terrible, but it's not the optimal one, okay? This is one barrier. Now, if we change it to some other values, okay? And notice that all I'm doing here, the only difference between custom weights and biases 1 and custom weights and biases 2 is simply the negative sign on the x and bias. And so what's the expected barrier if I change since I changed the negatives here? Does anyone have an idea of how the barrier will look? Yeah, please, Patrick.
Flip along the x-axis.
Yeah, it will be flipped along. Perfect. Flipped along the x-axis. That's much better than the way I would have put it. If we run it again, ideally, it goes flipped along the x-axis, right? So we have two different barriers, and they are different. One goes like this. One goes like this. The other one goes like this. And what we want is the ability, and so we have two different barriers. One goes like this, one goes like this. And you know what? It would be really, really swell if we could just add the two together, right? That's really what we want. We want the ability to add both of these particular boundaries together to get the sum of the boundary to get some sort of curve going, okay? So how do we do that? Well, we could do that by having two layers instead of one. Oh, yeah. Do you have a question?
I was just going to say, kind of take the intersection point and then just choose which one is better at their intersect. So if you have both of them, you just have the intersection points, and then whichever one is better up until the intersection point, you take that one.
So basically you're doing the method with the during the multi-class. Basically, the multi-class logistic regression lecture when we trained multiple logistic regression models, and then picked the one that was most confident for each class. That's sort of the same idea, right? Yeah. So that's a good idea, and you could absolutely do that. A little bit tedious. It is a little bit tedious, especially if you get a ton of barriers going. But that's excellent where your mind is at. I'm going to propose something slightly different. So what we could do is simply create a new model. So before we had a single perceptron that fed into the logistic regression. Now we just have two perceptrons, multiple with two weights. And actually, this should be like weight 3 and weight 4. That's bad for that. These are and bias 2. These are marked incorrectly. Sorry about that. But all we need to do is instead of having a single logit feeding into the sigmoid function, we just sum two logits feeding into the sigmoid function. So let's see what we get in that case. So how do we do this? Well, in code, well, all we really need to do is have all we really need to do is simply have both the barrier functions. So instead of having so in this case we have the first barrier function with the bias there, and this is the second barrier function with that bias. Remember the second barrier is the same as the first barrier except with the x value flipped, the x value and the bias value flipped. So we simply have these two barriers. We simply have these two barriers. We simply define a row for each one of the barrier functions, okay? And then we multiply this by x. And so what will this give us? This will give us z1 and z2. This weight matrix times x gives us z1 and z2. And then if we want to sum those two together, we simply, what do? We multiply it by a 2-by-1 matrix, okay? In this case, I am multiplying it by a 2-by-2 matrix, but I am simply doing that because the first row represents the positive class, and the second row represents the negative class. Okay. Again, we're using multi-class cross entropy, multi-class softmax logistic regression. So we have to have a output for each the positive class and negative class. So visually, we're thinking, what's the probability for the positive class? Because probability for positive class should be 1 minus the probability for the negative class. Intellectually, but in code, we have to have 1 for each. Okay, so that's the only reason for this second output. I have 2 rows because I need 1 row for positive, 1 row for negative. Okay, but otherwise, doesn't matter. Doesn't matter because to get the positive up there, I simply need to sum the two barriers together, and to sum the two barriers together, I simply multiply it by a 1-by-2 matrix. Yep, because Z is a 2-by-1 matrix, I multiply by a 1-by-2 matrix, and then that sums the two logits together. Does that make sense? So, and I don't put any biases. You could adjust the biases and stuff later. You could play around with it later. But that's all this class is doing. Basically, just having two different linear models defined, and then summing the two different linear models together, outputting them, and because we're using cross entropy, softmax cross entropy, that adds in the logistic function, and we get a particular barrier like that. Okay, we get a barrier. We have two different barriers represented by the black lines. Okay, there we go. We have these two barriers that are defined like so. And there is a bias shift because I am not doing the biases correctly. Well, I did put a bias in the first layer, so because of that, there's a vertical shift because of that. But the most important thing that I just want to emphasize is that by adding the two different barrier lines together, you get a curve, right? So hopefully seeing this, it'll become obvious why, if you add more barrier curves, you could get even more complex shapes going. You could get even more complex barriers going, even more complex separations going, right? Does that sort of make sense? So the reason we're doing multi-class, the reason we need multiple layers is because we want to define multiple potential barriers, and then we need another layer to sum those barriers up, okay, to get something more complex. And then if we want to go even more complex, like three layers, 4 layers, that's the same idea that goes more complex. Let's say we wanted to go to 3 layers. Well, if we have a barrier like this and another barrier like this, each of those, we would have 2 curved barriers on the second layer, and then we want to sum up those 2 curved layers into a super curved layer on the third layer. Does that make sense? So that's why multiple layers become important. And so this is just sort of a proof of concepts, but if we do something we could do something more complex. Now, I don't know how many of you caught this, but when I defined this model, I did one very important thing. And specifically, I separated these 2 layers by a particular, what's known as an activation function. We've discussed activation functions before, right? The sigmoid function is a particular activation function. ReLU is a particular activation function. An activation function is simply a nonlinear function that takes in a particular input and maps it to a particular output. Now the question is, why did I do this? Why did I separate the first layer from the second layer by a particular activation function? So let me answer that right now. Let's try what we just did without ReLU real quick, right? So we have the same multi-class linear regression, and all I'm doing here is commenting out the ReLU. Okay? So if I comment out the ReLU, what happens in this case? Well, if I run it, and I run that, then I get a straight line again. Okay? So I could promise you that I'm not doing any optimization here, right? I'm not doing any optimization here. Remember, in this model, I'm just manually setting the barriers in the first layer. These are my barriers. I'm manually setting them. These barriers are still the same. I'm still plotting these barriers here. Okay? But all I'm doing different is that instead of having some activation function in between these 2, I'm simply multiplying those barriers and summing them up and outputting them. Okay? So before, I had those barriers, I passed them through an activation function, and then I summed them up. Now, I'm taking the entire value of those layers and just summing them up and then outputting them. So doing the second thing, gives us something bad. Well, it doesn't give us something bad. It just gives us something that we don't want, right? It gives us the sum of the two. It gives us the sum of the two sum of the 2 barrier functions. But the sum of the 2 barrier functions is just a straight line, which isn't the curved line that we want. Isn't the curved line that we saw before. So what's so special about that activation function? Well, let's think about it. Without the ReLU, the output is simply first layer, goes into second layer, plus bias. Okay? In this case, we set the bias to 0. That's without the activation function. Then, if we do out the math, which we were perfectly able to, I mean, this is just a normal algebraic function. We could just do a normal algebraic, we could just sort of, we could just expand out the function. We could multiply W2 by W1x and multiply W2 by B1. And then so we get a new activation function that is W2 times W1x plus W2 times the first bias plus the bias to second bias. Okay? So if if we don't have anything between the layers. What happens is that mathematically, this is still just a linear function. Mathematically, this stays a linear function. And really, the model will just treat these two weights here, as these two weight matrices here, as a single weight matrix. It's just going to optimize it the same way that if we had just a single W here, single weight matrix here. It's going to optimize it the same way. It's going to stay the same. It's still a linear function. So you just are doing one big matrix multiply. And I mean, I guess you have a more complex bias, but a bias is just a single value. It's just a constant value. It's just going to shift the line up, down, left, right. It's not really going to do anything. So that doesn't help us. What's special about having an activation function, what's special about is that you break up the linearity of the model. So in the case of the rectified linear unit, remember, rectified linear unit was simply a activation function that if it took in a positive value, it just passed that positive value through. If it took in a negative value, it passed out a 0. Basically, it would never output anything less than a 0. The activation function looked like this, right? So in that case, so because this ReLU is not linear, its threshold's negative numbers, so it is a nonlinear function. Then you have a case where the new function becomes W2 times ReLU W1x. So this W2 cannot be passed through this ReLU function and just added to the W1x. Okay? So because of that, you have two separate layers. And because you have two separate layers, you get that curve. Okay? So ReLU bends the input space by zeroing out the negative components of the intermediate vector. And because of this, the network behaves differently in different regions of the input space. That's why you get that nice curve. Because in the left region, one of the barriers is prominent. In the right region, the other barrier is prominent. Okay, and that's because when one of the barriers becomes negative, the ReLU basically makes that barrier disappear. So you get a nice curve going there. So returning back to our dual half-moon example. And the code is long, so I'm just going to jump back to the notebook form. So returning back to our two half-moon example, knowing what we know, all we're going to do is define two different layers. Okay? We're going to define two different layers, and we're just going to make the intermediate layer some number of elements large. Okay? In this case, we're going to make the intermediate layer 8 elements large, right? So having I should say, I'm going to jump ahead. So all we're doing is basically we have a bunch of inputs, and now we're going to have a bunch of what's called intermediate layers or hidden layers. And then we're going to go and pass the outputs of these intermediate layers to the output layer. Okay? So we could choose really any number of elements. We could choose any size of intermediate layer in this case, right? In the case of the half-moon, in this particular case, we could choose a size of 8. It doesn't really matter. We still have an input size of 2 inputs. The input is 2-dimensional. We have an output size of 2 classes, okay? So we have a layer that's 2 elements. Then we have a hidden layer that's 8 elements. And then we have an output layer that's 2 elements again. So we define the model like so. And the most important thing is we add a nonlinear activation function in between the 2 layers. And so that allows us to have barriers combine in a way that curves the summative barrier around the classes. And then we optimize. In this case, we optimize. And so having 8 hidden layers means okay, so we do all of this. And so we get a function that looks like so, okay? Which looks pretty good, actually. It is a nice curved layer, and it curves around the classes, okay? So whereas before we had a single straight line, now we're effectively getting multiple straight lines, okay? So if we look more closely, if we look at the actual values of this weight matrix, if we look at the actual values of this first weight matrix, and then draw them, we will find that we have 8 different barriers defined by this first weight matrix, like so. So each of these black lines here corresponds to a different weight matrix. And then these black lines all sum up to give you a sum barrier that curves around the different half moons. That basically gives you a nonlinear class barrier in the 2D space. Okay? And actually, if you analyze this sort of single barriers here, you could, for instance, see the point at which these 2 barriers intersect is the point at which this barrier goes from going up to curving down. The point at which these barriers intersect is the point at which the total barrier goes from going down to curving up. Okay? So if you play around with this model, you could very easily see how having multiple linear barriers on the first layer gets summed together into one nonlinear barrier in the second layer. Okay? And then again, you don't necessarily only have to do 2 layers, but the idea is the same. If you have, for instance, 3 layers, the second layer would give you multiple nonlinear barriers. You could have one barrier that's like this. You could have one barrier that's like this. And then the third layer would sum up all those nonlinear barriers into a new nonlinear barrier, and so on and so forth. And that's how you scale up a model. Basically, you start off with a bunch of linear barriers. You get a bunch of nonlinear barriers. You sum those nonlinear barriers up into some more super nonlinear barriers, and then you sum up those super nonlinear barriers into a set of not exceptionally nonlinear barriers, and so on. Okay, that's the beauty of deep neural networks, that you could effectively construct very many different types of nonlinear functions from multiple linear functions. Okay? This is related. This comes up in many different aspects of computing. Constructing something nonlinear from something that is linear. This is basically the premise behind all computer graphics, right? Every single computer graphic, every single image we see is just a single triangle polygon, and then you put a whole bunch of triangles together and you get some 3D complex shape. Same thing here. You put a bunch of linear barriers together, you get some complex nonlinear barrier. You put a bunch of those together, you get something even more complex, and so on and so on and so on, all the way down the line. Does that make sense? Okay. Okay. So hopefully I've beaten, not hopefully, but I think I have beaten that horse to death. You could do any activation function that you really want. I think I've tried most of these activation functions, and they all work okay in the model, in the code above. So I would encourage you to try it out, to just change ReLU to sigmoid or whatever you want, and try to see what different activations give you. The major important thing is that the activation functions are nonlinear, which almost all activation functions that PyTorch gives you are. I don't think, I don't know if, I gotta check, is there a defined linear activation function? I don't think there needs to be, because you just sum things together, but I could always be wrong. It could always just be a function for the sake of it. But yeah, but PyTorch gives you a whole bunch of different nonlinear activation functions. Yeah, if you guys want to experiment with the code, just download it off the site. Just change this line. Just change the model. Yeah, change this line right here, line 11. Instead of ReLU, you could do tangent or sigmoid or whatever. You can see how that affects things. It does affect the model, but I mean, it still will give you sort of that complex nonlinear barrier. Yeah. Yeah, I think all of that makes sense. Any questions so far? No? Okay. So that is the concept behind that's the concept behind deep neural net. And let's go back to here. Come on. Oh. There we go. All right, so now back to some definitions. The model we created is known as a two-layer perceptron. The model we created is known as a two-layer perceptron. A individual weight-mate, a perceptron is simply one of the layers. Okay, so similar to that diagram we showed above, it's simply a perceptron is simply the concatenation is simply input vector is simply one vector being fed into another vector and then transformed by some nonlinear activation function. That is what's called a perceptron. The concatenation of multiple perceptrons separated by nonlinear activation functions is known as a multilayer perceptron for obvious reasons. Basically, you have bunch of linear barriers. You get a bunch of linear barriers at output here. You put a bunch of nonlinear barriers into this input. You get a bunch of nonlinear barriers into this, and so on and so forth. So every layer. So what's important is that even though it's not shown, every layer is followed by an activation function. Oh, come on. Every layer is followed by an activation function and is referred to as a hidden layer if it separates the input and outputs of the model. So all in the model, we have an input layer that simply takes in a bunch of inputs. We have that output layer that simply outputs some values, the probability that a class A input belongs to class K. And then all the layers in between those two are called hidden layers because you don't see them. You don't interact with them directly. Hopefully that makes sense. And every layer has an input and output dimension every layer has an input and output dimension that is a hyperparameter of the model architecture. And that's very important because, at least in the standard neural network models that you're going to see, you are going to see, I'm going to jump back to the model. Yep. Yeah. There we go. In the standard neural networks models there you see, the one thing you have to define is simply the size of your layers. Okay? You don't get to dynamically define the size of your layers after the fact. What do you think the computer would do? Let's say the computer allowed you to, let's say you said to your computer, you know what, not only can you change the weights inside the matrices, but you could also change the size of the matrices themselves as well. What do you think will happen? Yeah, please. Yeah, the computer would just make the matrices as large as possible because why not, right? So I mean, there are sort of evolution algorithms that basically allow you to change the structure of your model as you evolve things. But those typically you have to come up with some constraint for the size of your model. Something. There has to be some function that constrains the model size. So in this case, the simple neural network models we're considering, the only thing that you must define is the size of your layers, right? and the order and structure of your layers and all of that. Okay, so just the architecture of your model is the thing that you have to define, and then you could just set everything to start off as some random variable, and the computer will try to figure out if everything will work. But the size of your layers and the activation functions between the layers, you have to define that. What's actually kind of nice is that, did I put this here? Tau is trainable, right? Yeah. For some activation functions, you have parameters that you have parameters in the activation function that could be trainable. So tau, I think in this case, is trainable. There are some more complex activations that could be slightly adjusted by the optimization parameter, but that's a more complex optimization. Anyway, so with deep neural nets, your job is basically make sure you define the system architecture. That's it. So in this case, so in the previous instance, we defined a two-layer perceptron model. In this case, this would be called a three-layer perceptron model because you have 1, 2, 3 layers. Typically, you don't include the input layer in the sort of name because the input layer is just sort of copying what the input value, right? It doesn't really do anything. So in this case, this is a three-layer perceptron, and you could go on to like a 20-layer perceptron also, or 100, 1,000. Although there's a lot of diminishing returns on that. Okay, so last example, I promise. One more example. So one reason that multi-layer perceptrons are so good or are so useful is because, before we had arguably what was a beautiful but kind of simple classification data set. Okay? There are more complex classification data sets. So for instance, a classic one, besides the MNIST number data sets, there is the MNIST fashion data sets, which gives you a 28 by 28 pixel image of particular clothing items. And your job is basically to classify the image as, a pants, a dress, a sandal, a shirt, a bag, etc. 28 by 28 images. It's hard to believe that at one point in time, this was actually hard for computers to render. So this is a this is a huge data set actually. Did I write down? I don't remember the true size. Okay, I'm not gonna. Well, we could look. What was the true size? Fashion in this. Yeah, 10,000 examples. Yeah, or oh no. Oh yeah, it's 80,000 examples I think. 60,000 training examples. Test set of 10,000. Oh, I guess they want us to split the training into validation and training set. Okay, so 70,000 examples. They don't define a particular validation set. That's okay. So the MNIST. So this is what's called the MNIST data set. MNIST, like the National Institute of Standards. What does NIST stand for? What was the last word in the NIST? National Institutes of Standards, not weights. Standards and technology, right? Yeah, so national standards, they have a lot of such data sets. Everyone's familiar with the MNIST number data set. This is pretty much the same thing. You accept the fact that this is clothing items. The images are a bit more complex. But what's nice is that this is a 28 by 28 grayscale image of clothing items, and so that it's a relatively simple data set. So what we could do is simply create. There we go. We could create a model, and in this case, we could create a 3-layer model. Oh no, 2-layer model. Yeah, only a 2-layer model. Simple 2-layer model. We have an input dimension, which is 28 by 28, that's the number of pixels in the data set. We have some hidden layer dimension, and we have an output dimension. So the output dimension is the number of classes. In the case of the MNIST fashion data set, there are 10 classes: shirt, shoes, bag, pants, pullovers. I'm forgetting a bunch of them. I think it differentiates sandals and sneakers, something like that. But there are 10 output classes. There are 28 by 28 inputs, so that will give you 784 input dimension. And then there's some number of hidden, then there's whatever you want your hidden layer size to be. So in this case, we're going to make our hidden layer size 128. Why? Because it seems to work pretty well, but it isn't too big. And so we define, again, a two-layer multi-layer perceptron model where first layer goes from the input to the hidden layer, which is the input dimension to the hidden layer 1, that matrix. And then we have some particular activation function which we defined as, in this code, ReLU. Again, you could come here and change the activation function of the hidden layer. And then we have a second layer, which is hidden layer to output. So we have 10 output classes, so that's why we need the output dimension to be 10. And then the hidden layer, so it comes from the hidden layer, so whatever the dimension of the hidden layer is, has to be the first dimension of the matrix weights. And by the way, this matrix here corresponds to the weights in between the nodes, right? I think everyone has that, but that always confused me when I was first learning this, that the matrices correspond to the weights in between the nodes and not these nodes themselves, okay? These nodes themselves are the actual outputs of the matrices, of the matrix multiplications. Anyway, so simple two-layer perceptron. I mean, there's nothing special that we did here. The only other thing is that we're using a data loader to upload the MNIST data sets, and we're downloading the MNIST data set from Torch Vision, okay? So, by the way, so if you run this code, don't get annoyed, but if you run this code, it will download the fashion MNIST data set to your local folder. That's how the Torch Vision works. Basically, you call this function, it sends a request to, I don't know, the Torch servers. I don't know who maintains the Torch servers. And so you download the actual fashion MNIST data set locally, and then you run everything. It's not very big. It's only a couple megabytes. So simple two-layer perceptron. We define our data loader to give us batches of images. So we're doing stochastic gradient descent over here. So this is how we train our optimizer. So again, for every batch, we zero the grad. We calculate the predictions by inputting the batch into the model, and then we calculate the loss by doing multi-class cross entropy loss on the predictions and the actual targets of the Y batch. And then we calculate, and then we do the loss backwards, and we do the optimizer step. All of this is very standard code that you've seen before. And so if we run through this, we get a particular decrease in our loss, a significant decrease in our loss. Our loss starts out at 2, which is pretty high, and it ends around 0.0015-ish. And then our training accuracy goes from 34% to almost 100%, as does our validation accuracy goes to above 80. So it works pretty well, right? So multi-layer perceptrons work pretty well, but there is a slight problem. And the slight problem is that with the fashion MNIST data set, you had an image that was 28 by 28 pixels large, right? And the reason that the pixels is so grainy, because you want the input to be small, because you're just trying to learn neural networks and you don't want to deal with the training on GPUs or anything yet. So you need to have small images so you can train these things on your CPU. The issue becomes when you need to figure out larger images. So for instance, if your image is 256 by 256, and the output of this layer has an identical size, then how many weights would be necessary? There would be around 4 billion weights necessary. I don't know if you guys keep in track of LLMs, but the small LLMs have on that order of magnitude. There's the most popular small LLM, Llama 7V, has 7 billion trainable parameters. And I could promise you that a simple 2-layer perceptron that has 4 billion parameters, even with 4 billion parameters, is nowhere near as useful as a large language model with 7 billion parameters, okay? So all that is to say that, in theory, you could probably conquer any problem by just having as large a simple multi-layer perceptron as possible. But there are limits. That's why we have algorithms for computer science. Not everything can be handled through brute force. So that's what we're going to talk about next time. We're going to talk about we're going to talk about convolutional neural networks, which is sort of the next newest architecture to handle complex data, handle large data inputs. So that's all we have for today. Homework and midterm grades will be posted today or tomorrow. Everyone did really well, so yeah, don't worry about it. But yeah, it will be posted today or tomorrow. Project descriptions will be posted within the week, and then the architecture behind evaluating the projects is still giving us a little bit of difficulty. So that's the reason for the delay. But we'll post up the descriptions at minimum within the week. So thank you guys for coming today, and I'll see you on Thursday. Thanks, guys. Yeah. All righty.